Hello and welcome. This video is an introduction to EMMALAB, a standalone app created using MATLAB App Designer that is used to perform an end-member mixing analysis, or EMMA, on a mixture dataset. This video will not explain what an end-member mixing analysis is, but will rather introduce the workflow for performing this analysis as if the user understands these concepts. Before using the app, your data must be set up appropriately so that the data may be read into the app properly. Here is the included template, with columns representing different variables that are used within the app. The required format for the data will be explained later. The following identifier columns must be filled with data in order for the application to work: sample location, data type, and sample date. In addition, the columns starting from column 9 onward must be filled with the user's chemical data, and there must be at least 2 columns of chemical data. Columns 4 through 11 are left for the user if they desire to use those variables for plotting time series data, but may be left blank. Please note that the user should not change the names or position of the first 3 columns. Of the required identifier variables, sample location, data type, and sample date, the format of the data is simple. In the first column, the name of the location where the sample was taken should be placed. Another column may be used to place unique identifiers to the data, but should not be used for this column. For example, I would like to represent a body of water that we'll call Grand River, which I collected 100 samples from a single location and would like to perform a mixing analysis. Each sample may have its own unique name, such as Grand River Sample 42, but I should simply label the sample in the sample location column as Grand River. The next required column of data is the data type. For this column, all of the locations that I would wish to perform EMMA on would be labeled as mixture with a capital M, and any end member I had sampled for the analysis would be simply labeled as end member. The last required column of identifier data is the sample date. If the user collected multiple samples in the same location on a single date, only one sample from the sample date should be used. Otherwise, these samples should be classified differently within the sample location column. With any of the elemental data that I had collected, that would be placed starting in the 9th column, meaning column number 9 would hold the first variable of chemical data that the user would wish to use in the analysis. Please note that all chemical data should be included in however many columns are required. For example, if I measured 40 different chemical variables, I would place all of the data on this spreadsheet regardless of whether the variable was thought to behave conservatively or not. This will be decided later on the app, and elements may be included or excluded in the analysis within the app itself. As a note, if the user includes chemical data with some symbols, such as the greater than or less than sign, or just 0, the app will automatically replace those values with the minimum value in the column divided by 2. If this is not desired by the user, all symbols or 0 values should be adjusted by the user before submitting the data into the app. After filling out the spreadsheet with your own data, it should look something like this. You may want a more detailed spreadsheet if you would like to plot certain variables on a time series plot. If all of the required columns are filled out, save the file, then you are ready to use the app. When you are ready to start the analysis, launch the app. This introduction window will appear, and to start, the user should select the Data tab. Click the Load Dataset button and a dialog box will appear, listing the files in the current folder. Navigate to the data organized following the template. Select the file and press Open. Your data will automatically populate within the table to your right, and your defined locations and end members along with the range of sample dates will appear on your left. Use the date drop-downs to select the date range that you would like to include in the PCA and EMMA. I will just use the default, which is the full extent of the data. Additionally, you may select here which locations or potential end members you would like to include in the analysis. Theoretically, you might begin this process with a handful of end members that you believe may explain the mixture data but are not yet sure. Including any number of end member will not affect the results of the PCA, so a good rule of thumb is to first include all potential end members. They may be removed before the mixing calculation, which will be shown later. However, at least 2 end members must be selected in order for the mixing calculation to work. After the desired date range, locations, and end members are selected, click Set Preferences, and the indicator light will change to green to show that the preferences have been set. Now we will set plot options for our location or locations and our end members. The location or locations on our dataset will appear in this location box to the left. In our case, there are 3 locations that we would like to include in the analysis. In many cases, the user may want to only view a single location. Either cases will work within the analysis, but we will use the 3 locations in this example. There are several plots that are used to display the data within the app, and each location and end member should be classified differently. Here, the user may define the appearance of the location and end members by selecting a symbol and a color. I will use a single symbol, the circle, to represent my locations and differentiate between the locations using color. Now I'll do the same thing, but for the end members. To assign a symbol and color to each end member, I will select the End Member button under the Data Type box, which will automatically refresh the above box with the names of my end members. I will choose both different symbols and colors for each of my end members. At this point, if I wish to save the categories I've defined by the locations, end members, and date range that I've selected, I would click on this button, Save Preferences, which will open a dialog box which allows me to name the file and save it as a MAT file. This allows the user to skip through the first steps if the application is opened again. To upload the save file in a different session, simply click the Load Preferences button, navigate to the previously saved MAT file, and click Open. Note that from uploading this file, the preferences are set. Now that the different locations and end members are categorized by symbols and colors, I may begin to decide which of the chemical variables in my dataset may be used as tracers. Click on the Correlation Matrix tab, which shows a bivariate scatter plot of our mixture data points within our selected time frame. The default with the app is to only show the first 2 variables in the dataset, and the user may iteratively include or exclude the variables they believe may behave as tracers. There is no strict guideline to what relationship on the scatter plots indicates a truly conservative relationship, but generally, if the trend of the data is linear, then the variable may be considered conservative and used in the analysis. After the tracer set is chosen, we may continue to the PCA tab. This plot shows the initial spread of the data in 2-dimensional PC space or U space using the first and second principal components, with the locations and end members as defined in the Plot Options tab. Here, the user may continue to alter the tracer data to influence their decision with the mixing analysis. The PCA plot and %explain table will be automatically updated by the removal or addition of a single end member. The end members may also be averaged together to view their position on the PCA plot by selecting the Averaged End Members option within the End Member View panel. From here, the user may decide which end members sufficiently circumscribe their data to perform the mixing analysis. The user may also view the data in 3D to observe the spread of the data and how well the end members circumscribe the data cloud by clicking on the Rotate View option to view the data at different angles. The Residual tab contains the ability to create residual plots for each of the selected tracers and a scree plot. The user should select the number of principal components they wish to include in the analysis, select the tracer they would like to create a plot in the drop-down, and then click Calculate. The residual plot will appear on the plot below. Many studies use these plots to determine the number of principal components to include within their mixing analysis, where if there is structure in the residuals, the structure may diminish by iteratively increasing the number of principal components used to represent the data. This feature is mainly important for those who wish to perform their calculation in U-space, but we suggest a separate method that will be explained later. To create a scree plot from the current PCA, simply press the Scree Plot option in the Plotting Options panel and the plot will update. Additionally, the PC scores for the locations are shown on this tab with their sample dates for easy viewing. If the user wishes to use this data outside the app, they may click on the Save PC Data button, which will prompt the user to insert a name for both the coefficient table and the PC scores tables. Both are saved in separate CSV files to the current folder. Once the user decides which end members circumscribe their data, they are ready to perform the mixing calculation. If you included more end members in the initial view than you would like to include in the final calculation, simply navigate to the Data page, deselect the end members you would like to exclude, and click Set Preferences. Then navigate to the Plot Options tab and click on the removed end member to remove them from the analysis. Back on the mixing calculation page, you can see in the mixing summary under N members in analysis which N members are being used in the calculation. You may also review the locations and tracers that are being used in the analysis to ensure that these are the variables you would like to use in the mixing. Next, you may decide the method in which you perform the mixing calculation. We would recommend performing the mixing calculation in tracer space, that is, using the standardized or z-scored original data for the mixture and N members in a system of equations. This minimizes error in the calculation by including more information than is retained in the principal component score data. However, if the user would like to perform the calculation using the principal component scores or in U-space, the option is available to calculate using either the first 2 or 3 principal components. When you have determined which calculation to use, click on the Calculate % Contributions button. Notice the calculation status light turns red and will turn green once the calculation is finished. We used MATLAB's function fmincon to calculate the mixing, the specifics of which can be found on the supplementary file or under the script analyzeemma.m. The table to the right will update with the mixing calculations, with the first column showing the location, the second showing the date, and the rest of the columns showing the name of the N members and the fraction contributed to the mixture for the given sampling day. Each N member in a row adds up to 1. The user may choose to plot these fractional contributions on a stacked bar graph under the Mixing Plot Viewer tab. Select the location of interest from the drop-down and select the Plot % Contribution over Time button. The plot to the right will be updated, with time on the x-axis and fractional contributions on the y-axis. A common method to check for how well the mixing model predicted the fractional contributions accurately is by taking the mixing contributions and calculating what the contributions of the various tracers would be for an individual mixture sample given only the fractional contributions of each N member. Select from the drop-down the tracer that you would like to see whether it was predicted well by the model. Select Plot Prediction and wait for the plot on the right to update. The table below, the Plot Prediction button, will update and show the r-squared, slope -1, and y-intercept for the observed values plotted against the predicted values. To view other tracers, click the Clear Plot button, select a new tracer from the drop-down, and press the Plot Prediction button again. The plot and table will update with the new tracer predictions. To check the error within the N-member sample sets themselves, we use the method of jackknifing the mean of the N-member datasets. This method can take a long time to complete, especially if the user's N-member datasets are large. The process that occurs here is that each N-member dataset has one observation iteratively removed, replaced by the average of the remaining samples, and is continued with every sample. Each new jackknife value is then treated as an averaged N-member used in the mixing analysis. For example, if I had 10 precipitation samples, I would have averaged all of those values together for use in the mixing analysis, as is done in the app. With this technique, the jackknifing creates 10 new averaged together values, which we then treat as 10 different averaged N-member datasets to use in the mixing calculation. If I had 3 N members, each with 10 different samples, then we would take each sample from each N member and create every possible combination between the jackknifed averaged N member values and calculate the mixing result. For our example of 3 N members and 10 samples in each N member, that would be performing the mixing calculation 1,000 times. Every possible combination of the 3 N members is calculated for a single sampling day, averaged together, and the standard deviation taken. How much these results deviate from each other is the result used in the error analysis. Thus, if someone had 3 N members but with 50 samples each, the mixing calculation would be performed 125,000 times. Depending on the number of cores the computer has, this calculation could take quite long to complete. The user should keep this in mind when considering this error option. In our example, we use a significantly reduced dataset of 3 N members, each with only 3 samples. To begin the error calculation, select the Calculate % Error. The status button will change to red and will change back to green once the calculation is complete. Once the calculation is finished, the time elapsed box will update to the amount of time in minutes the app took to complete the calculation. With the River dataset used in the paper, there were 10,000 different iterations and the calculation usually took around 6 hours. To plot the error, select the location you would like to view under the drop-down and select the Plot Error button. The average input of the N member along with the error bars for each N member is plot over time. Additionally, if the user would like to save the averaged fractional contribution values and standard deviations from the jackknifing, the user may use the Save Jackknife Data button and assign a name for both tables, which will be saved as CSVs to the current working folder. At this point, the steps within the mixing calculation are complete, but if the user would like to observe general time series trends in their data, you may use the Plot Viewer tab. This page will allow you to view any of the variables on your original uploaded spreadsheet and view their relationships over time. The default x-axis value is the sample date, and the y-axis may be changed to any variable. By selecting a variable, the plot will automatically update with whichever location the user initially chose to include in the mixing. Additionally, the x-axis, y-axis, and title may be manually adjusted by the user. To save any graph within the app, hover your mouse over this icon, and a drop-down will appear with options to save the graph as a PNG file, to copy the image to the clipboard, or to copy the image as a vectorized graphic. We will save our image as a PNG by clicking on the first icon. We'll insert a name for the file, and then click Save. The image will be saved to the current workspace. This method may be used to save any graph throughout the app.